The purpose of this subsection of the notes is to give a general overview of other topics in time series analysis that we simply just don't have time to get to in a one-semester course. Some departments of statistics will actually offer a two-semester sequence of time series analysis. Not too many departments, but some will. Also, you will see time series analysis taught outside of a department of statistics, such as in a Department of Economics and a Department of Finance, because the great majority of the applications of time series analysis are in those particular areas. Books such as Shumway and Stouffer also are set up to do like a two-semester sequence of time series analysis too. And so again, this is why there's just not enough time to get into all the very interesting things that time series analysis allows one to do. So to begin with here, we're going to take a look at what are called threshold models. Again, more comprehensive accounts in Shumway and Stouffer's book, and especially in Howard Tong's two books on it. He's basically the one who's thought of as originating this area. And basically the idea of a threshold model is as follows, that you can imagine observing a time series over time. So you're maybe observing an x of t. Then once x of t gets to a particular point, let's say a threshold in terms of its value, the underlying, let's say, modeling mechanism that creates then the numerical values of the time series, they change. And so what this allows one to do then is to have, let's say, multiple time series models based upon when one reaches a threshold corresponding to x of t's numerical value. So we're going to talk about here very briefly threshold autoregressive models. So based upon what the value is at time, let's say x of t minus 1, that corresponds to which type of autoregressive model you're going to use corresponding to a time series. So you can think of, let's say, x of t minus 1, let's say if it's greater than or equal to some numerical value, as the threshold. And so what we can do here is actually divide up the data into, let's say, R mutually exclusive and exhaustive regions, denoted by R sub 1 through capital R sub little r. And then for each region, and some regions might actually share the same model, for each region we have the following autoregressive model. So this is for, let's say, region J corresponding to our time series. To let you know whether or not you are in region J, we can look at x of t itself. If that hits, if it meets a particular threshold, then it's in that particular region. Now note here, I mentioned x of t here. Well, I maybe mention x of t minus 1 there. It's the same idea. I just decided to write the model in terms of x of t. So of course, if little r is equal to 1, that means that we have just the usual AR model. We only have one region. Then model estimation, identification, diagnostics can all be done separately within each region. So as an example, Shumway and Stouffer gives a data set corresponding to the number of deaths from pneumonia and influenza that are actually observed. And so this is what the actual time series looks like, where the first differences are plotted on the y-axis. We have time on the x-axis. And the authors chose to use a threshold of 0.05 here, corresponding to this particular data. And so once we reach this 0.05 point with our numerical time series, then we switch to a different model. Once x of t goes below this value, then we switch back to the original model. So they chose to use then this particular model here, where they actually do phrase it in terms of x of t minus 1. So we have two different models, and so you can see that the same model can be used for different segments of the time series. Okay. Now the next topic is what's referred to as intervention analysis. The basic idea is this. We want to be able to account for special events that occur, or what we will refer to as interventions, when modeling a time series data set. In particular, what this area focuses on, we want to know if this special event or this intervention had, let's say, a significant effect on the time series. Well, where would this be important? So, for example, with the OSU enrollment data, I mentioned how Oklahoma State University decided to open up a second campus for the university that was actually based in Tulsa. And as you might imagine, if you're going to open up another whole campus for a university, then enrollment numbers should hopefully be increasing. And so to account for that, one could incorporate what's called an intervention variable into your time series model. Another example corresponds to, let's say, maybe we're talking about a particular kind of cereal at a grocery store. And that company that makes that cereal decides to run a special promotion to try to drive up sales. Well, in order to know if this special promotion actually did drive up sales, what one could do is actually incorporate an intervention variable into the model to account for the fact that there's this new promotion. Another example is, let's say a new law is enacted by a city, a state, or even a country, and they want to know if with this new law, has there been changes associated with it? So, for example, a number of years ago, it became mandatory to wear seatbelts in cars. And so to measure the effect of actually having people mandated to wear seatbelts, we could introduce an intervention variable into our model to account for that and test for significance of that variable. And that will help then people in government know, did this new law work to help prevent deaths? So let's suppose that the intervention occurred at time capital T. Is there evidence of change then in x of t? And so in a very simplistic setting, what one could do is observe x of t for all the time periods up to time period capital T minus 1, and then for all the time periods from capital T all the way up to n. We could denote the mean for the first time period as mu sub 1. We could denote the mean for the second time period as mu sub 2. And in this kind of a setting, if we had, let's say, actual independence for our x's that we observe, we could do a simple two-sample t-test to test for is there a difference in the means. However, it's not that simple because the x's, generally speaking, will not be independent. And so this is where then an intervention analysis then can allow us to do essentially the equivalent to a two-sample t-test when we have our data not from a random sample. So with intervention analysis, I mentioned that we're going to include intervention variables into our time series model. This is what these intervention variables could look like. We could have a step function, which basically says up until right before you're at time point capital T when that intervention occurs, the step function is simply 0. Then once the intervention occurs, you step up to 1. So essentially it's an indicator variable, 0 before the intervention, 1 after the intervention. We could also look at what's called a pulse function as well, which basically says only at that time point of that intervention do we have a value of 1, otherwise it's a 0. Now, the pulse function can actually be written in terms of the step functions. So if I take s of t minus s of t minus 1, I get that pulse function back. Often as well, you will see people just in general to represent a step or pulse function by the letter I sub t for the intervention variable. Also, very frequently, you will hear people referred to as the intervention variables as an input. So you're inputting something like a new law, and then the responses to that intervention variable are their outputs. So what has happened corresponding to this? Well, let's talk about then the possible responses. So I guess you could say maybe the simplest response is as follows. We could have a fixed unknown impact omega. This omega is actually a parameter that we will want to estimate. The impact is felt b periods after the intervention. So in other words, we could have something like this with a step function. Omega times our backshift operator raised to the little b power times that step function. So to give you an idea of how this works, suppose we have a scenario such as follows. Maybe at capital t equal 5, we have the intervention occur. Maybe this is, let's say, at time point 5, a particular company that makes a cereal has decided to do an advertisement for it, to promote it, to see if it could drive up sales. And so our step function would look like this. But maybe we understand that, hey, the effect is going to be delayed. Just because somebody, let's say, sees maybe an advertisement on TV on a particular day when that starts, doesn't mean they can go out to maybe the grocery store to go buy that box of cereal. So let's say it's delayed by one time period. And let's say the effect is 3. Maybe we're looking at the sales of a particular cereal at a particular store, and we're measuring it over time. So then, the response then would be 3 times s sub t minus 1, where in the superscript here in parentheses we have information about when that intervention occurred. So if we look at this simple table here, we can see the effect that this has. So at time point, let's say 2, well, s of t would be 0 because, let me page up here, because s of t is equal to 0 when t is less than 5. In terms of the response, now I'm looking at 3 times s sub 1 because I need to go back one time period, as you see there. And so thus the response is 0. And I could keep on going. Suppose I go to time point 5. This is when the intervention actually occurs. What's the response? Well, 3 times s of 4, which is still 0, because we had that delay by one time period. Then finally at time point 6, again the s of 6 is equal to 1. Now we get 3 times s of 5, and now we get the effect of the corresponding, let's say, new promotion. So another kind of response that we could have due to an intervention is that maybe perhaps the response is sudden, but then also an additional effect is more gradual. So that's what this represents here. So we have our omega times the backshift operator raised to the b power again. We have a step function, but now we're going to divide by 1 minus delta b, where delta b is 0, where delta is between 0 and 1. And so in other words, we have this additional component here, and if we think of this as actually the result of a sum of an infinite series, then that means for us then that now we have this representation here for the response to the intervention. We have omega times the step function at time t minus 1 plus delta times the step function at time point t minus 2, and so on. And so what this is representing here is that we have delta times b raised to the 0 power. Here we have delta times b raised to the 1 power, and so on. So if we had delta equals 0, then we have essentially what we had in the previous case. And of course, if you have delta equal 1, then you're going to actually run into problems here. So let's take a look at an example. Suppose that, again, the intervention occurs at time point 5. We have a step function, b equal 1, omega equal 3, delta equal 0.5. And if we go through the process of writing what everything is out, notice that time point 6 then, this is when we're going to have that first effect. We're going to have a response of 3. At time point 7 then, we're going to have a response of 3 plus 3 times 0.5, or 1.5, and we're going to have a response of 4.5. Where all I'm doing is writing out then the corresponding terms. Oops, let me go up. That we see here. Well, now I lost my pen ability to write with a pen. We lost. Let me start over again. Basically, what we're doing is we're writing out these terms in this infinite sum, corresponding to when we finally observed at least t equal 5 for that subscript for the s. Here's then also a nice plot. This comes from the Box et al. Book on time series analysis that illustrates what happens with potentially different formulated responses to an intervention. So far we've talked about this one and also this one, but you can see, and you can go through this on your own, how there could be different kinds of responses, and depending upon how you formulate your corresponding response, you can meet a lot of different scenarios. Now, one could actually also have multiple interventions, so not just necessarily one intervention variable to have with our excuse me, not just one intervention variable. One can have other types of responses, I should say, with that particular variable. And so here now we have, kind of like what we've seen before, let's say an omega operator and a delta operator that corresponds to this response. Now we could also have multiple intervention variables. This is what I was trying to get at as well. And what we can do is basically say our model x of t comes about through k possible different interventions, where I just use I here to represent in general intervention, plus some additional parts of our model, which is what we normally have been using in the past for our ARIMA model. And so this is just a way to represent again how x of t comes about, beyond just only saying in a ARIMA model, we also include the intervention variables into the model itself. Now, the process or the part of the model that's without the intervention, which is what we focus on a lot in this course, in this particular case is not as important. Rather, what's important is what's the effect from the intervention itself. Is there like a significant impact? And so because of that, then the regular old ARIMA part is often referred to as a noise process or a noise model. And we can find what an appropriate model would be for this by looking previously before the intervention, taking that data, find the best model, and then you have to make the assumption now after the intervention that still underlying noise model is still going to hold, plus some now new effect from the intervention. And as I said, hypothesis tests for the parameters associated with the intervention are often very important in this situation. Often it's the prime importance, the thing that's primarily important. Okay. So in terms of modeling, I think actually I've already discussed this. Work with an ARIMA model. Try to find an ARIMA model before the intervention occurs, and then use that model still after the intervention, plus the effect of the intervention. Now, how can you do that? Well, that's where the XReg argument, I should call it argument, not option, This is where the xreg argument can come in to try to incorporate the response to the intervention and the intervention variable. So for example, you might do something like this for an intervention variable where, let's say, it starts to be observed at time point 80 out of 100. Also, one additional aspect of intervention analysis, you can use this to account for outliers that you can't figure out how else to account for. So for example, a pulse function could be useful in this situation. Now, another interesting topic in time series analysis is what's referred to as transfer function models. More extensive references are located there. And basically now we're going to think of, let's say, explanatory variables that are observed over time to try to predict our response variable of interest. So this has some similarities to, let's say, working with regression models with ARMA errors, but this is set up in a different way. So where could this be of interest? Let's say we have information for the OSU enrollment example. We have information about the number of high school graduates in a particular year. We can maybe use that as an additional variable in our model to try to forecast future enrollment. Maybe we have, let's say, the amount in advertising that a company is using to try to promote a particular product. We could use that to try to forecast sales or understand sales. And as you might expect, based upon what I just said with that previous example, basically all the intervention analysis examples that we talked about before are special cases of transfer function models. Okay, so some general concepts associated with this. We have what's called an input series. This is like our explanatory variable. It's measured over time. We're going to call it x of t. We have an output series. That's y sub t. That's like our response variable. We're going to assume stationarity for x and y. Note that x of t is a numerical quantity. It's not necessarily simply only zeros and ones like what we saw with intervention analysis. And the idea is that we will expect that that x will affect what y is over time. And along with this, there are going to be additional things that could affect the variability for what y is, and that's going to be referred to as our noise model. And it's essentially similar to what we saw with intervention analysis. This is our regular old ARIMA model. So our transfer function model then is this. Y sub t is equal to this nu of b operator, which is just this linear combination of the nu's with the backshift operator, times x of t. So again, think of x of t essentially as an explanatory variable. Its effect on y sub t is measured by these nu's through time. And then we add to this our noise model, which we're going to call n sub t, which would be our regular old ARIMA model that we would have used perhaps otherwise. These nu's here are often referred to as impulse response weights in the terminology that's often referred to as, or in this area. And what we like to be able to do is estimate these nu's. And the way that we do that is that we say this operator here is basically formed in this manner, which is very similar to what we saw with our intervention analysis. We have these omegas, we have these deltas. Now, how do we choose, though? Why do I want an S? Why do I want R? Or in terms of what should R be? What should S be? How do we choose that? Well, this ends up actually coming down to looking at the cross-correlation function to make those kinds of decisions without going into all the details. So here's a classic example that's often used in these particular settings. This actually comes from Box's book on this subject, or on time series analysis in general. And what this deals with is, let's say, a gas furnace. X of t is going to be the input gas rate. How much are we feeding into the furnace? And then Y sub T is going to be the carbon dioxide output from the furnace. So it's essentially a response corresponding to how much gas is actually put in. And basically what we have is data that's measured over every 9 seconds. And with their particular data, what one could do is fit a model to it. We have a noise part of our model, and then we have the part of the model corresponding to the transfer function additional component. And without going into all the details, this is a model that I estimated to this particular data. So what we see here is that we have this ARIMA part, and then we have the remaining part that's worked with X sub T. Now also with this Y sub T, I said, well, let's say that I ignore having this input, this gas rate. What would be the best model for Y sub T? And what I found the best model to be was in ARIMA 302. And so based upon that, I decided to go ahead and plot what the corresponding model would give us along with the actual observed data. Also do the forecasts with the corresponding confidence intervals. And this is what I got. And so the black corresponds to the observed data. The green corresponds to just a regular old ARIMA 302 model alone, what would be the forecasted value. The red corresponds to what the transfer function would forecast the value to be for the carbon dioxide. And then I think what really is really cool here, and do note that this is actually a zoomed in version of the previous plot, so I didn't mention that. What I think is really cool here to understand the benefits of using the transfer function model is that this orangish yellow coloring here corresponds to 95% confidence intervals for the forecast at each time point. The blue corresponds, and that's from the regular old ARIMA model, the blue corresponds to what I would get from the transfer function model. And what we can see here is the blue gives narrower intervals than what the yellow is. And so we can see then what the benefit is of incorporating additional information here, the gas rate. I get tighter confidence intervals, and these are actually, I failed to mention this too, these are actually 95% intervals. Okay, so that concludes this very short introduction to some other topics that one will find in time series analysis.